Hello everyone. In this lecture, we are going to consider multiplying a distribution by a smooth function. The space dimension will still be 1 for the sake of simplicity. So in order to solve a PDE with smooth coefficients in the sense of distributions, one has to make sense of the product of a distribution by a smooth function. If you have a PDE with derivative with distributions and the derivatives of distributions and the coefficients is smooth, then such a product arises naturally. So let's first define what it is. Okay, so we consider T a distribution and F be a smooth function, C infinity function on the open set I. The product of T by F is given by this formula. So as before, we are going to pass the operation to the test function so that everything is well defined. For instance, here f is a smooth function and phi is a test function, so that the product of these two f phi will still be a test function. And therefore, the second term, the term on the right-hand side is well defined. And hence, the left-hand side is a finite number. It is clear that such an operation defines a linear form. And is it a distribution? And turns out it is. Let's give a short proof of it. So since T is a distribution for any K compact set in I, there exists a constant C, a constant M, such that if we consider ft phi, we know that it is nothing but T applied to f phi according to the definition of multiplication. And this constant will come into play. So here actually for any phi test function with support in K. And according to this the fact that T is a distribution, we have the bond C times supremum K, little k, no negative integer less than or equal to M, and F phi to the K. Uniform norm. Okay, so this is just the definition or the equivalent definition of T being a distribution. So now we want to prove that the product is a distribution. In other words, on the right-hand side, we should have the same kind of formula, but with only phi in here. So for that, to this end, we're going to separate the operator of differentiation on f and on phi. And we're going to pull the f, derivatives of f out of the supremum norm. Okay, and this can be done by applying Leibniz rule. We know that it is going to be C. So here is it's a basic formula for J from 0 to K for the product. So now the Leibniz rule says that this formula, the case derivative of the product of two smooth functions is given by the sum of the combinatorial coefficient K choose J, then F choose J, F, the J's derivative of F times the K minus J's derivative of phi, uniform norm. And of course, we can use triangular inequality to prove that. Okay, so C supremum on K, sum J from 0 to K, K choose J, triangular inequality, and further we can do this. J. All right. So now we can change the name of the constant. Okay, we're going to still call it C, but the value changes, which incorporate all the values in here and the combinatorial coefficient, and to say that we have eventually also this kind of bond for J, for phi, for the derivative of phi. And this finished the proof according to proposition 1.5. Okay, so now indeed this operation product by a smooth function defines a distribution, which is cool, because we are still working within the class of distribution if we multiply a distribution by a smooth function. So next we consider a couple of examples. First, some basic properties, and which says that this new operation of multiplication is consistent with what we call product of two smooth functions. The first one is fairly easy. It says that if you have an L1 log function, we know that automatically we can find, we can associate it with a distribution by an integral form. And we have f, a smooth function, then f multiplied by the distribution associated with the L1 log function g is equal to the distribution associated with the product of the two functions fg. Okay, and fg is still L1 log function because f is smooth. So this is really easy, and we can see it by apply just the definition. And secondly, we also have that if we have two smooth functions and t distribution, then we can apply the multiplication, right? We can multiply t first by g, then by f, or we can multiply t by the product of fg, so we end up having the same distribution. So this is also easy to show by using just the definition. Pass the multiplication to the test function, then we can see that these two coincides. Okay, the third one is quite important. It's called Leibniz rule. Okay, as in the case of smooth functions, Leibniz rule is a widely used rule, right? When we do calculations, and we just did it in the first in the proof of the fact that f times t is a distribution, right? So let's give a short proof of this fact. Leibniz rule. Right, the rule takes exactly the same form as they do for smooth functions, so it's easy to memorize. And the way we prove it is also not hard. Okay, so let's do the case n equals to 1. So we're going to show that ft prime is equal to f prime t plus t prime f t prime. Okay. For that matter, we're going to apply it to a test function phi, for any test function, and we have, firstly, we're going to use the definition of a derivative. We pass the derivative to the test function with a negative sign, and then we can use the definition to have this. Next, we realize that this is nothing but, okay, so now we can apply Leibniz rule for smooth functions for this guy, and to write it as a difference of f phi prime minus f prime phi. Okay, so we end up having t prime f phi for the first term, right? So here, together with t and the negative sign, it's like we pass it back to the distribution, so we have t prime applied to f phi, and then plus t applied to f prime phi. Okay, so now we can reverse the multiplication. Okay, put it back to the distribution side, the function, so that we have t prime, so f t prime plus f prime t phi. And this shows that ft prime is equal to ft prime plus f prime t, which is exactly Leibniz rule in the case n equals to 1. All right. So in general, the formula can be shown by induction. Okay, I leave it as an exercise. All right. Now let's continue. So now we consider a bunch of examples. So the first one is pretty simple. So we consider a direct mass. Okay, so the distribution is direct mass at 0, and the function is a smooth function. So this is a well-defined object according to our observation in here. Right? So in this part. Also, what is distribution? This distribution turns out to be quite simple. It's a constant times the direct mass. All right. Okay, let's do this verification. It's fairly simple. Example 3.3. So we have a smooth function f, and we're going to show that f delta naught applied to a phi function is equal to f phi, f naught, phi naught. And so it is the constant times the direct mass applied to phi, right? According to linearity, you can put it in. This is what we want. So this proves the first example, and the second one is slightly more interesting. So we know that. So now the Cauchy's principal value 1 over x multiplied by x gives us back the constant function 1. So this is a second example. Now let's do this. So first we have x, right? So recall that Cauchy's principal value, right? So PV 1 over x phi. So it is the limit, right? A limit of this and the x larger than epsilon. Phi of x dx, and as we shown last time, it can be written as integral from 0 to infinity, phi x minus phi negative x over x dx. Okay, it's a well-defined object because phi is a smooth function. Okay, so in this case we are going to consider x PV 1 over x, right? Applied to a test function, we should have PV 1 over x applied to x times phi, okay? And we're gonna make use of this formula, and which says that the integral 0 to infinity, and on the numerator is the value of the function on the point x minus the value of the function on the point negative x. So the value on the of the function on the point x will be x phi of x, okay? Because we have passed this x to the test function. And then plus x phi of negative x over x dx. So we can do some simplification. We see that it is the integral of phi x plus phi negative x, and by a change of variable, it becomes the integral of the whole of the function on the whole real line. And this is nothing but the constant 1, okay, is the distribution associated with the constant 1 applied to phi. Okay, and this is what we want to show. All right, so now we are going to investigate some more theoretical properties of the operation product by a smooth function. And we're going to start with polynomial, the simplest polynomial, which is a linear function. All right, so let's consider this, the proposition 3.4. It says that linear map given by t is a distribution, maps to t multiplied by a linear function, this operator, this is also a linear operator, is onto. And also, the linear operator has a null space composed of only those direct masses multiplied by a constant. Okay? This is quite a useful fact which can be used to solve differential equations, for instance. And here I'm gonna reformulate this proposition here a little bit to be more precise. So firstly, we have that the operation is onto, which means that for any S distribution, there exists a T distribution such that x minus x naught times T is equal to S. Okay, so this is exactly onto of the operation product. Secondly, we have something to say about its null space. So in other words, we're going to show that if this guy, the multiplication of linear function and t is equal to 0 with t a test function distribution, then t has to be a constant times direct mass on point x naught. Now, this is another way to reformulate the proposition on the range of the operation and the null space of the operation product by a linear function. Okay, let's give a proof of this. Oh, let's first show the second point. All right. By hypothesis, for any test function phi, we have t applied to x minus x naught phi equals to 0. Okay, this is the same thing as this equation in here. And our idea would be, so in order to argue that t has to be a direct mass, multiple of a direct mass on point x naught, the idea is that we're going to make a decomposition, right? So t, any psi, so now for any psi test function is a test function. We're going to make a decomposition 1 plus psi 2 in such a way that it has certain properties, right? So like that psi 1 can be written as this for some test function. On the other hand, we'd like to have t psi 2 equals to what? Equals to phi of x naught times c, right? Why do we want these two properties? If we can show that such a decomposition exists, right, for any test function, then t applied to psi 1, t applied to phi becomes t applied to psi 1 and t applied to plus t applied to psi 2. And t applied to psi 1, because of this property of psi 1, will be 0, according to the hypothesis. On the other hand, if t applied to psi 2 gives us a constant times phi of x naught, we are done because it says that t applied to psi will be precisely this value, and this is exactly the same thing as this equation we want to show. So all the work is reduced to find such a decomposition. So let's proceed. The second one is easy, so we're going to choose psi 2 to be the constant phi of x naught times any test function. Okay. Then when t applied to this function, we're going to pull out the constant phi of x naught and times t applied to chi, which gives a constant. So the second requirement is fulfilled. We still want to have the first one, and we're going to add another property to the function chi later. So we'll see what kind of property we need. So then 2 satisfied, 2 okay. Then necessarily psi 1 is psi minus psi 2, which is psi minus phi of x naught chi. Right? In order that first is satisfied, we are going to choose, we're going to let another requirement on the value of chi function on x naught. We want it to be 1. And then the first also okay. And this is due to the following fact. A function, any test function. So let me use another notation. Maybe test function theta is not is equal to 0. Theta is a test function. If and only if theta x can be written as x minus x naught times phi with phi in di, a test function. Okay. So this shows that the first property is okay for the following reason. If we have chi of x naught is equal to 1, which means that psi 1 of x naught is equal to psi of x naught minus okay, wait a minute. The value is psi. So we choose. Okay, so it's a psi. The function is called psi. So it's a typo. Psi. All right. So psi 1 on the point x naught would be equal to 0 if we choose chi of x naught equals to 1. Okay. And according to the fact, it is equivalent to say that this function can be written as a linear function times a test function. And this is what we want. Okay. And so this shows that the 1 is all right. So it remains to prove this fact. So this fact is fairly simple fact. So if we have a function which takes that value, so this direction is simpler, right? So if function can be factorized as a linear function times a smooth function, a test function, then when we plug in the value x naught, we have automatically 0. Okay. The other direction, when we have theta takes the value 0 at x naught, then we can define phi to be theta x over x naught. And clearly, clearly the second property is satisfied. It remains to check this guy is a test function. And it is a test function for the following reason. Since theta of x naught is 0, we can safely subtract the 0. on top. And by the fact that theta is infinity with compact support, we see that this function is also test function. And this is done. Okay. So we're good with the second property, which says the null space of product by a linear function, right? Degree 1 polynomial is composed of constant times Dirac masses on x naught. Let's now to see how to prove the first one, the first property. Okay, so the first property we want to find a T distribution such that for any test function we have the following. Okay, so this is precisely this equation. Now we want to find such a thing. So the idea is to define T on a generic test function to be S applied to a certain transform that I call Q of psi, in such a way that the operator Q fulfills several requirements. And the first requirement, requirement A, is that Q maps test function to a test function. And this is the minimal requirement. And secondly, we want it to be linear and continuous. Okay. And the third one would be that if we apply psi equals to functions of this type, then Q of psi would be phi, so that we have fulfilled the equation. All right. Here. So last one, Q applied to this gives us back phi. Okay. Let me explain why do we need these kind of requirements. Firstly, we want this guy to be a test function. So this says that eventually we obtain a test function, so that the right side is the distribution applied to a test function with a finite object. And secondly, if Q is linear and continuous, we have that the left-hand side, so as a linear form on the space of test functions, it is linear. Okay, linearity guarantees that on phi it is linear, and continuity guarantees that on phi it is a linear form. Right, it's a continuous linear form, so that this defines the distribution. And finally, as we said, we have we can get back this equation, so that we finished. Okay, the proof is very similar to the when we show the onto property of a derivative operation on the space of distributions. So let's do this. The third property actually is the most informative, and from the third one, we can already guess what this Q should be. So for any psi test function, we define Q of psi to be let's put in here Q psi of x The idea is that we're going to take the ratio of psi and x minus x naught, right? So this kind of the inverse operation of this of this, right? And we can we cannot make sense of it because this will not fulfill the first requirement in general, right? If psi of x naught is not zero, then there's a singularity 1 over x minus x naught at the point x0, so that this is not going to be a smooth function compact support, right? So we have to make some adjustment. One idea is to subtract its mean value, the value on x naught of this psi function. Okay, psi of x. So if we do that, we are not going to have a function with compact support because of this value. If this value is not zero, okay, so then outside of the support of this outside of support of this function psi, so we have a constant hanging there divided by something which is not zero, okay, so that the support will not be compact. So this is not so good. So still we need to do a further adjustment, which is to multiply it by a test function chi. So this will do the work with chi in D. So now this guy becomes a test function. Okay. If further we assume that a chi of 1 is chi of x naught is equal to 1. If chi x naught is equal to 1, then we can kind of forget about this term. So this guy is clearly a test function, right? Without the chi. Without the chi around the x naught, I mean, it's a C infinity function. Okay. Let's do the justification of this. Take 1 minute. It's not plus. There's going to be x naught and 1 minus chi of x over x minus x naught. Okay. This property. And indeed, we show that this guy will be a test function if we have a test function chi satisfying the fact that this property takes the value 1 at the point x naught. There's no singularity on the point x naught because of this requirement on x naught. 1 minus chi of x will cancel the singularity. Same thing here, right? Same thing here. This doesn't matter, and the support is also it will be compact because of this representation. C infinity with compact support, so it's a test function. The first requirement is satisfied, right? So first requirement is all right, and secondly, it is a linear. It is clearly a linear form, and we can show that it is continuous. Right? The topology of convergence on the space phi on the space of test function is super convenient, right? It says that you have uniform convergence for all the partial derivatives, including zeroth derivative, which is the function itself. So these things can be used to show that Q is actually also a continuous operator. And thirdly, so let's check C. Thirdly, we're going to show that when Q is applied, this operation is applied to a function of this type. In such a case, we realize that this term will not appear because the value of this function on the point x naught will be exactly 0, so that cancels this term, and it remains only psi over x minus x naught, and then multiplied. It remains only this function divided by x minus x naught. It remains, so we have phi, right? So the third property is also a simple fact. And this finished the proof. Okay. Now that we have finished a theoretical result, we would like to apply this result to solve a differential equation. And this is the content of example 3.5. We have a fairly simple differential equation, first order one. So x multiplied by t prime plus t is equal to 0. Right? This is a homogeneous equation, and we can solve it. So first we example. First we do realize that this operator is equal to xt prime by Leibniz. So here we have used the Leibniz rule, and hence the equation can be written as the derivative of something is equal to 0. And this way we know how to solve it. This means that it's equivalence, right? So xt must be a constant, or okay, so the distribution associated with a constant. We can call it TC or just put a C over there. And then since we have shown that the null space, the null space of multiplication by a linear function is given by direct masses. So the direct mass may be solution, right? Direct mass could be the solution if C is equal to 0. Okay. So the solution would be so the ones that solve this plus the ones which solves the homogeneous equation. So the T is given by constant times delta naught plus under our other solutions, which we can see actually from this example that we see already here. Principal value 1 over x multiplied by x gives us a constant 1. And we're exactly in this form, right? So that actually if we plug in principal value, we have 1. In other words, a constant times principal value solve the equation. And if it is harmless to add some direct masses because multiplied by x, direct mass takes 0 value. Okay, so eventually the solution, the non-smooth solution of this equation, are given by this the linear combination of direct mass and principal values. Okay. Now let's see next question in this example. Next question in this example, we see it's not homogeneous anymore. So if we put an S on the right hand side, right, given an S distribution, show that there exists a T such that the differential equation is solved. This is a fairly simple exercise after we have understood the onto property of this multiplication. So the second question equivalently says xt prime is equal to S, right? And we know that there exists a solution which solves this equation because derivatives onto, as shown by previous lecture. So there exists a distribution such that xt is equal to that distribution, and then we solve. Okay, so onto so that there exists a S tilde, say, so xt is equal to S tilde. So now, using our proposition, we know that there exists a S tilde tilde such that t is, there exists a t, there is t such that xt is S tilde, and it's done. So we find a t which solves this equation, eventually we solve that equation. And that's what we want. Okay, so I'm done with this example, 3.5. We realized that previous proposition handles only degree 1 polynomials, and we would like to generalize it to polynomials of any degree, right? So we can It's quite a natural question to generalize that thing to any degree, and we can indeed do this. But in order to prove an upgraded version of proposition 3.4, we're going to make use of the following quite interesting and useful identity about direct masses. Okay, it's a kind of differential equation actually for the k minus 1's derivative of the direct mass on x naught, right? So the derivative of that guy times x minus x naught is equal to a constant times that distribution. There are many interesting identities about direct masses, and this is the one we're going to use to prove a generalized version of proposition 3.4. Okay, let's do this. Lemma 3.6. Proof. Lemma 3.6. So we consider a generic test function, and so we are going to consider left-hand side, delta x naught case derivative of that apply to phi, and this according to the definition x naught case and x minus x naught phi. Okay, and then we can make use of definition for the derivative, so x naught, x minus x naught phi, the whole thing case derivative. Then for handling this term, we're going to make use of Leibniz rule. Okay, Leibniz rule says that the case derivative of a product of two smooth functions becomes the sum of a combinatorial coefficient times the j's derivative on this function times k minus j's derivative on this function. We realize that many of the terms will vanish because if we take derivative more than 2 on the linear function, we're going to have 0. Or if we don't take derivative at all for this linear function, then when we apply the direct mass to the right-hand side, we're going to have 0 as well because this guy remains, right? So the only term that does not vanish is the one when we derive one time for the linear function, so that this becomes a 1, and the k minus 1 times for this the test function phi. And in that case, we have a coefficient k choose 1, which is k, and we're going to have phi k minus 1 x naught as a result. And this guy can be written differently, right? So -1 to the k minus 1. We put it together with the derivative k minus 1's derivative of phi. It becomes the following: k minus 1's derivative of the direct mass on x naught applied to phi. Okay, and this shows that this is equal to, okay, let's complete the whole thing, negative k delta x naught k minus 1. And this shows that this guy is equal to this guy. And we're finished. Okay. So once we know the lemma, I think we are ready to generalize proposition 3.4. Still 2 points. Firstly, so now we're considering proposition 3.7. So we consider any non-negative, okay, so any natural numbers n. And we're going to show that the linear map that maps a distribution to the product of a distribution by a polynomial of degree m is onto whose null space is composed of linear combinations of direct mass on x naught and its derivatives up to the order n minus 1. Okay, and the first property is pretty straightforward. The onto property is straightforward because we can actually apply our proposition 3.4 m times. We can rewrite this application as follows: minus x naught to the m. T can be written as such. We do this at m times, multiplication m times t. Okay, so every time we multiply it, we can find, so if we put it to be s, then firstly we can put all these guys together and we can find a distribution such that the guy in the parentheses is equal to that, satisfy this equation, right? And then we apply the same trick again and again till in the end we find a t. This is easy. So proof of proposition 3.7 onto is easy. So now we are going to show that the null space is composed of linear combination of direct masses and its derivatives. So firstly, m is equal to 1 is done. The case m is equal to 1 is done in proposition 3.4. Assume by induction that m for generic, the formula holds. Okay, the formula holds this formula actually. So what I'm saying is T equals the linear combination Ci direct mass x naught as derived I from 1 to m minus 1 holds for this equation, solves this equation, right? And we're going to show that, so these are the only solutions that solve this equation, okay? We're going to show that the same kind of formula will work for a higher order polynomial, higher degree polynomial. Consider, in other words, we consider this equation, x minus x naught to the m plus 1t equals to 0, which is the same thing as saying that x naught m, x minus x naught t. Okay, this is the basic property that we showed in the beginning. We have associativity is equal to 0. And since this is true and we have assumed by induction that this guy, the only solutions of this equation is given by the linear combination of direct masses and its derivatives. So this actually gives us the following formula: x minus x naught t will be I from 0 to m minus 1, Ci delta x naught I. Right? So here's where this beautiful identity about direct masses kicks in. We can actually upgrade the derivative to I plus 1 according to this identity, right? So if we consider a derivative of the order k minus 1, we can replace it by that with the sacrifice, when we sacrifice a polynomial and a constant, right? So this is what we're going to do. So for each of the term, so it's equivalent again. T is equal to I from 0 to m minus 1. So now we're going to change the derivatives of direct masses. It becomes delta x naught I plus 1, right? And with a negative sign. negative sign and ci over, I think it's gonna be I plus 1, and this will be x minus x naught. Okay, and now we can put things together, and we have by linearity that t plus sum of, okay, let's do a variable change. We're gonna call this I plus 1 the new I, so that we have I, so here's 1, 0. So I from range from 1 to m, and ci minus 1 I delta x naught I is equal to 0. Okay. Now we can apply our proposition 3.4. The null space of product by a linear function are given by the multiple of Dirac masses on x naught, so that we're done. So t will be eventually, there will be additional zero order derivative of delta x naught, so I from 0 to n, ci minus 1 I. This I doesn't make any sense, so I'm gonna separate this. I'm gonna separate this. So it's gonna be a constant, whatever, c naught delta x naught plus higher order. All right. So this is what we want to prove. Right. So indeed, not only the formula, this the proposition works for first degree polynomial, it also works for any degree, polynomials for any degree. All right. So next question would be, can we do more general functions? So here's the question. Can we do generalize this property, this onto property to all smooth functions? Okay, the answer is no. Indeed, the question arises if you have a lot of zeros, say. So when the function takes constantly zero value on the interval I, then the multiplication of f and t will give only zero distributions. Okay, we'll give only zero distribution. So it's not going to be onto. It works for a polynomial because actually polynomial on this, it takes the value 0. So all the polynomials have only here, we consider that as having only 1 0, right? With certain multiplicity. And we can generalize this property actually. So this is the content of our let's say the main result of this section. So if we have, this takes us a bit ahead, but let's say it's quite consistent with what we're doing. This is the main result. So if we have a smooth function such that all these zeros are finite order, okay, something like this. If a is a 0, then there exists an m such that the m's derivative on a is not 0. This kind of function, so it basically says that a function, there are, so on any compact set you have only a finite number of zeros. This the behavior is not too peculiar. There are not too many zeros for the smooth function, so that we can still show the onto property, right? So this is the this property clearly, this result theorem 3.11 clearly generalize what we know about polynomials. Okay. I forgot to mention, but actually the proof for polynomial can be generalized to any polynomial, right? So if a multiplication, you have a generic polynomial which is not identically 0, then you can do the factorization so that it can be written as the product of this kind of term. Okay, so by using proposition 3.7 several times, we're going to show that this guy is actually onto. And the null space, again, we're going to use this several times, then the null space will be composed of the linear combinations of direct masses on the zero of the polynomial P. Right? A is a zero of the polynomial P, and is derivatives. And the order of the derivatives is corresponding to the multiplicity of the zero. This is trivial extension of proposition 3.7. And what we're going to do in the theorem 3.11 contains more information, right? We're not necessarily having a polynomial type of stuff. So that is where the new examples can be applied and could be useful for solving differential equations. Okay, so the goal would be to give a proof of the theorem 3.11, and for that matter, we need a sort of a localization argument. And here's some preparation for that localization argument. Now, first of all, I'm going to define the so-called restriction of distribution on a subset. And this is definition 3.9. We are given a distribution. So here now I have actually two intervals instead of just one. So I'll be careful. So this is our first interval. Let's call it I. Let's call it I. And there will be another interval. Okay, so draw it in parallel way so that they do not overlap. Let's see where they are. This is J. I and J. So T is a distribution on I. And the restriction of T to an open subset of I, J, right? J, open subset is called a J, is a distribution given by this formula. Right? This formula is nothing really. So T restricted to J applied to a test function. See that now the test function's support is contained in the open set J, which is a smaller set, right? That's why so in order to define the restriction of distribution to a smaller set, we only need to consider test functions on the whose support is contained in the smaller set. And so we still pass the operation to the test function, but this time what we do is to make an extension. So T is applied to test functions defined on I, but phi is only a test function defined on J. So what we do is to make an extension. Let's say this is our test function. We have a test function which takes the value, something like this. So this test function is defined on, it's not quite accurate. This test function is something like this. It takes the value 0 inside it, outside of the interval J, so that its support is contained in J, right? So what do? We want to make an extension of this guy on the whole interval I by taking the value 0 outside of J. And this defines clearly a test function on I, so that this operation makes sense. This is what we call a restriction of a distribution to a smaller set. The point is that we only examine its interaction with test function on the smaller set. Okay. Now we can prove a following result. It's quite an interesting proposition. It says that if you have a sequence of, so here we have a sequence of open intervals, and the sequence is increasing in the following sense. an-1, bn-1 is the interval in-1, and next interval will be strictly larger on both endpoints, right? So an is strictly less than that, and bn is strictly larger than the right endpoint of in-1. So if you have this increasing sequence of intervals, open intervals, and the union of in is equal to I, right? It's still open, so I can be defined in such a way if we have a sequence already. And we can also we assume that there exists for each in there exists a distribution on in called Tn, which is consistent in the sense that the distribution on the larger set Tn plus 1 is defined on I plus 1. The Tn plus 1 restricted to the smaller set In is equal to Tn, which is the distribution on In. Okay, if we have a sequence of this kind, which is consistent, then we can find a unique distribution. T on the union of everything, such that we can recover the whole sequence by taking the restriction of this unique distribution on the biggest set, okay, by taking T restricted to In. So this is quite useful. So we call it a localization because when we consider I to be the whole real line, we can think of In to be negative n and n, so that we have a sequence of increasing and bounded intervals, which recovers the whole real line if we take the union. And this boundedness is very useful because we can have then the closed interval a and bn will be a compact set. A compacity helps us a lot in many situations. So in order to show a property, that is true, we can find first consider the restriction or the localized version of the problem to a smaller set. Find a solution and find actually a sequence of solution in a consistent way. Consistent, I mean this property is satisfied. Then eventually we have a solution to the problem for the whole set. Okay, so the sequence of the problem for the whole set, and this is how we're going to make use of this proposition. Okay. So let's see how we can prove this fact. Proposition 3.10. So we already know that there exists. So these are our data is a sequence of intervals, which is increasing, and I is the union of everything. And we also have that sequence of Tn such that the Tn plus 1 restricted to In is equal to Tn. So consistent sequence of distributions. And then we want to show that there exists a distribution on the biggest set, right? So and we can't do that because first the existence. We can show the existence by letting T phi to be just T and phi for any phi. Actually, for any phi in the I, so necessarily there exists a K in I such that the support is in K, right? So this is the definition of test function. So this is a compact set. Since it is a compact set, and we are considering interval as choice in this color, we are considering this interval I, which is largest. We have a compact set K in here. This is the K, and we also have a sequence of interval In, which increases eventually to I. So there exists such an interval I. So AN. So there exists IN. So here's the proof. There exists IN such that K is included in I. And IN is an open set. Okay. If this is true, then by the consistent property, right? So if IN, then by the consistent property, we know that T phi can be defined as any. So N phi, N plus 1 phi, etc. So by this consistent property, we see that after a certain n, the distribution does not change its value when it applies to phi. This phi has support containing k, right? So that indeed, this is well defined. For any phi, we can define this way. We can find the largest n such that we can find a certain n such that In contains the support of k, so that the sequence actually is a constant sequence eventually. Okay, so this is well defined. And secondly, we're going to show uniqueness. So if there are two, right, there is S also satisfy the property such that S different from T and S restricted to In is equal to Tn. Since they are different, there exists a phi function, a phi test function, such that S phi is different from T phi. Okay. So that we have S applied to, okay, then there exists a phi, and also there exists an n large enough so that the support of phi is included in In, okay, as before we have argued. And this means that this yields the following. This yields that S applied to phi is equal to S applied to phi is equal to here is equal to Tn applied to phi. It's different from this. On the other hand, T also satisfies this property. So Tn applied to phi. So we have a contradiction. Okay, so there indeed, if we can find a localizing sequence which is consistent, then we have a global solution, say, to a certain problem. And this is how we are going to prove that theorem 3.11. Let's just recall what we're going to prove. We have a f function which is a smooth function, and always zero have finite order in this following sense. Then we are going to show that this approximation, this application, product by smooth function is onto. Okay. Let's do the proof. Theorem, proof of theorem. 3.11. So there's only one theorem in this section. So we are going to prove, split the proof into several steps. So the first step, let's call it the reduction step. Okay. So imagine that we can't find a sequence. Let's assume, right? Assume that we can find a sequence of Tn. So these are all distributions on, so each of them is on In. So In as defined before, such that Tn plus 1 restricted to In is Tn. And also, we'd like to have a solution to the problem, which is to say, so fix S distribution on I. We show exists a T distribution on I such that F T is S. Okay, so this S is fixed, and we're going to find a T, such a T, and through a localization argument. So we assume that we can find a sequence of Tn, which is consistent in this sense. Also solve that equation, a localized version of that problem. In other words, when we restrict our function f to the interval in multiplied by Tn, we have s restricted to in. Okay, so here's the first thing. Imagine that we can find such a sequence. Then what do we have? Right. Then what we have is the following. Then by existence, part of proposition 3.10, we have there exists a T distribution on I such that T restricted to in is Tn. Okay, so that f restricted to in times Tn is equal to s restricted to in T restricted to in, which is nothing but ft restricted to in, and this is equal to s restricted to in. Okay, and if this is true, then by uniqueness part of proposition 3.10, we have necessarily ft equals to s, and the proof is done. Okay. This is because the right hand side we have s equals to, so another way to write it, we can define it as Sn. Okay, so we do have a sequence of distribution, Sn this time, sequence of distribution which is consistent in the sense that Sn plus 1 restricted to In is equal to Sn. Okay, by the definition, this is a simple fact. And since we have such a sequence, and we know that the SFT restriction to in solve this kind of equation, and we have uniqueness, S also solve the equation, which means that these two guys must be equal. So this finished the exercise. Okay, so conclusion. But we haven't defined such a sequence, right? So the step 2, we're going to try to set up the problem. So first thing we're going to do is to consider alpha beta a compact set inside this interval I. So now we have a compact set, and if we consider the zeros of the function f inside the compact set is it is compact, right? Because the function is continuous, so the inverse will be a closed set, and the bounded also. So we have compact set. So let A be a 0 of f, meaning that f of A 0 of f of order m. Meaning that f of A is equal to 0, and also by Taylor, f of x can be written as x minus a to the m, and we have a 0, 1, 0, 1, m minus 1 factorial, 1 minus t, m minus 1, f m a plus t x minus a dt. Okay, by Taylor expansion we have this formula, and also because we have this the zero of the zero of f a is of the order m, meaning that the first derivatives all vanishes, so we don't have that. The point is that we can actually write a function as a polynomial type times a non-zero function. Right? This function will not be zero at least around the point A. So here's the crucial point. And this guy, is not zero in the neighborhood of A. Let's call the neighborhood J A. It's open neighborhood of A. By continuity, right? Meaning that this takes the value f x is different from 0 on the set JA removed A. Okay, and we can actually do this for all the zeros of x of f inside the compact interval alpha beta. So by capacity, there exists only a finite number n such that alpha beta 0 set is covered by union of JAI, right? So we can find a subfamily of these open intervals which covers the compact set I from 1 to n. So n is finite. This is crucial. So we actually we actually find that the zeros inside the interval alpha beta, there's only finite many. Why is that? Which means that there are only finitely many zeros. Because outside of the interval, because f of x is different from 0 for any point which is not in the union of J, union of this union of JAI. And also, it is not zero. It is not zero if for any x inside this JAI union when you remove the center. Okay, so the only point on which the function takes the value 0 will be those AIs, and there are only finitely many. And this shows that f can be written as a polynomial times shows that written as a polynomial times a function g, where g never takes the value 0 on the interval alpha beta. Okay, so now fx can be written as a polynomial on alpha beta times a non-zero, a non-vanishing C-infinity function, so that this either takes value positive all the way positive value or all the way negative value. Okay, so this is quite important because we have reduced the problem to something that we know, which is a previous proposition 3.7, which says that multiply distribution by a polynomial of any degree, right? So we can it defines an onto operator. So this is good. So this is the setup, and now we can make use of all this observation to finish the proof, and record it by. If we manage to find such a sequence, we're done. Such a sequence, consistent sequence, solving the problem locally, then we're done. So now we try to start constructing such a sequence. So this is step number 3. Okay, we construct Tn. So firstly, first observation would be that there exists a solution, any solution. So there exists a T naught such that when we find this solves the problem locally, in the sense that f restricted to I naught, T naught, the product is equal to S restricted to I naught. Okay, this is due to this observation. So eventually we can write f as a polynomial times the g, and we know how to solve that. So g is this never bother us, right? This function never takes value 0 on intervals. This will not bother us, and this we know how to handle. It is onto operation. Okay, so we do have a solution on subinterval, which is bounded subinterval, and also there exists a T1. Let's call it T1 tilde because it does not quite satisfy the properties we wanted. So we're going to make some adjustment later on. So, but anyway, so at least we can find such a solution which solves this. Okay, so this means that if we take alpha beta equals to I naught or alpha beta equals to I1, we have separately two solutions according to these two localized version of the problem. I1 this time. Okay, so we can find it. So the point is that this two distribution will not be consistent in the sense that T1 tilde restricted to I naught will not be equal to IT naught in general. So we have to do some small adjustment. Now here's an observation. If we compute T naught minus T1 tilde restricted to I naught and then multiply it by I naught, F restricted to I naught, we have necessarily 0. Observe that we have this identity, and this is simple, since indeed F restricted to I naught, T naught minus, so this guy is the left hand side is equal to this minus F restricted to I naught, T1 tilde I naught, and we have the left hand side we have S restricted to I naught, and the second thing we have actually F restricted to I1, T1, the whole thing restricted to I naught, and since we have the solution in here, so that it becomes this guy becomes, this guy is nothing but S restricted to I1. So clearly the restriction operator would satisfy this property. Anything, any I smaller than J, we have as I, right? Or also equal to S restricted to J, then restricted to I. So we make use of this this property to say that eventually this guy becomes 0. This is the first observation. So if this is true, then necessarily T is equal to T naught minus T1 tilde restricted to I naught will be a linear combinations of the derivatives of direct mass, right? It's going to be, we're going to call it J, I, so A, J are the zeros of the polynomial that we can find in here, and I are the order of the derivatives, okay, which depend on AJ, and J will be finite. Okay, so this actually says that we are not too far away. So although the property that there is the consistent property is not satisfied, when we do the restriction of T1 tilde to I naught, we do not find it precisely T naught. But up to direct masses, we are getting back to T naught. So if these coefficients say are all 0, then we have exactly the consistency relation. So now the adjustment that we are going to make is the following. So find U1, which is the distribution on I1, such that we are going to choose U1 to be such a U1 restricted to I naught gives us this whole thing, right? Gives us this whole linear combination of direct masses with derivatives. And also we would like to have that U1F restricted to I1 is equal to 0. Then if such a U1 exists, then we can define T1 to be T1 naught. T1 naught. Let me see. So T1 naught plus U1 satisfies T1 restricted to I naught equals to T1 tilde restricted to I naught plus U1 restricted to I naught. And since the restriction satisfies this property, and so we can have T1 restricted to I naught plus T naught minus T1 restricted to I naught. This cancels and we have T naught. Very good. So this is exactly what we want. We have the consistency property for this new T1, and it remains really the very last thing we want to do is to find such a U1, right? If we want such a U1, we show that there exists such a U1 such that these two properties are satisfied. Let's look at the second property, this property here. So this property we know actually, since U1, so when f is restricted to I1, it becomes automatically a polynomial times a non-zero function, right? So the solution of such equation exists. We can find a U1 which will be the linear combinations of direct masses of the zeros of f inside I1 and its derivatives. So that since all the zeros of f inside I naught will be zeros of f inside I1 because I1 is a larger interval. So all these guys will also appear in the solution which solves this equation. Okay, so this guy is the linear combination of exactly this kind of term plus some other kind of direct masses which correspond to zeros outside of the interval I naught. If this is true, then we're okay, we're done, because when we do the restriction, we can throw away those direct masses outside of the interval I naught, and we get back exactly this one. So the proof is finally done. All right, so let's wrap up what we did into this lecture. So we have covered first, the definition of multiplication by a smooth function and some basic properties. Examples, Leibniz rules are always important. We have nice examples like this. Also, we have shown that such operators onto, which is a special case of this, which again is a special case of this. And it's important to know that the null space is composed of direct masses, basically. And for higher order polynomial, we have a linear combination of direct mass and its derivatives. Same thing here, and all these are actually special cases of the theorem. And we also have this new localization argument, which can be used elsewhere to prove interesting results. Okay. Okay, it remains actually only one thing, and this part is a truly easy thing. So up till now, we have all considered equations, say, let's see, equations in this example. In this example, we have equations of this kind when we put the smooth function in front of the highest order derivative And then we can find actually non-smooth solutions such as direct masses or principal values. This is what we did for this example. And some different phenomena would occur if we put this S function, for instance, this smooth function, not multiplied by the highest order derivative, but multiplied by something else. Then we realize that now if we put A together with T instead of T prime, then the only solutions to satisfy this equation would be C1 solutions, right? So try this out. It's really simple. And if you have any question, just let me know during the online meeting. Okay, see you in another video.